Sorry, guys, I forgot to hit the record button. Sorry to interrupt.
Okay, no worries. So we're going to start off with a brief intro into Brookes Bell, what we are, who we are, what we do, and then we're going to get into the subject matter of NDT and the new innovations and advancements in corrosion mapping and thickness measurement for marine applications. So without further ado, we'll start the first slide. So in way of contents, this is just comments for part one, so a brief introduction to Brookes Bell. So we've been operational for almost 120 years now. We started off as a marine surveying firm in Liverpool, and we've since then expanded into a diverse range of disciplines covering marine engineering, right the way through to cargo science, materials testing, and analytics. So whilst we started diversifying in the UK, we then achieved global reach in the past 15 years. And we now operate out of offices in the UK, but as well as Shanghai, Hong Kong, Singapore, Houston, and Miami. Most recently, Houston and Miami. So in the midst of prior to the pandemic, we moved over to the States, and we have established a presence over there, and also operational in North America as well. Asia was several years ago, and we have experts who are active in all regions and sectors to do with forensic engineering, analysis, and marine casualty investigation. We also carry out routine condition surveys and technical dispute resolution and other expert witness work. So here you can see the company history and the timeline. So things got pretty busy after the year 2000 when we expanded globally. And again, as mentioned before, this is the spread of our offices. So our headquarters is in Liverpool. We have Naval Architects Centre of Excellence up in Glasgow, and we have a Centre of Excellence down in London. So the organisation of the governance of the firm. So on the top tier, you've got our executive committee, and on the second and third tiers are the regional and sector-specific directors of discipline. So our core MO, what we offer is a one-stop approach, and we have SMEs in a whole range of disciplines. So as you can see here, marine engineers, master mariners, naval architects, scientists and fuel chemists, those guys, the metallurgists and NDT specialists, fire investigators and coatings experts. So I'll give you a brief overview of the different disciplines. So I appreciate there's quite a bit of text here, so we will get to the good stuff relatively shortly. And if any of you would like further information on the other services the company offer, then we can send this through as a separate set of slides. So we have marine engineers, all of whom have served as chief engineer, and since coming ashore, continues to investigate a wide range of machinery failures. Nautical services is our master mariners. So the nautical services is twofold. So it's master mariner related issues, and also salvage and wreck removal services. So you have a case study of a salvage and wreck removal that we were involved in 2016. One of the other main disciplines in Brookes Bell is science. So our scientists are, whilst they're specialists in their own subject matters, they are classed as generalists. So cargo science is our number one stream of work for the for our scientists, but they do also specialize in anti-fouling and coatings and biofouling assessment services too. These are some of the brochures that are available for the various science disciplines. Naval architecture. Naval architecture is one of our core disciplines. We have a centre of excellence up in Glasgow, and these guys are tech savvy and are experts in subjects like computational fluid dynamics and stability assessments and various other advanced technologies. We also have a crew of fire investigators. So these are pretty busy globally and attend fire investigation, marine casualty scenes all across the world, and often couple up with other disciplines such as our metallurgists, master mariners, to work in close cooperation to get a full picture of the situation that has occurred. Metallurgist. So metallurgy is one of our core disciplines. We have 3 metallurgists, soon to be 4, that are subject matter experts, and they're supported by a team of laboratory experts focused on microscopy and forensic analysis of material failures. And this is my specific domain of expertise, inspection and non-destructive testing. So I joined Brookes Bell just over 6 years ago, and since joining Brookes Bell, I was utilised mainly in forensic analysis and marine casualty investigations in the first instance, and then what we saw was an opportunity to use our expertise that we'd gathered through years of forensic investigations and offer not just extent of damage assessments and condition surveys, but also preventative measures and technologies to provide solutions and perhaps prevent these kind of catastrophic failures that we usually get engaged in investigating from taking place in the first instance. So we've developed a range of technologies, some of which we're going to go into quite some detail pretty shortly. Fuel testing is another pretty new area of expertise for Brookes Bell, with the opening of the laboratory last year. Whilst our engineers have been involved in bunker claims we saw the need for further analytical capability and a service that wasn't offered anywhere else in the world with such aim as to analyze bunker claims specifically and complement our fuel investigation service. So we have various fuel testing capabilities and fuel chemists and bunker specialists within the wider company. We have coatings experts who make a part of our science department. Paint and coatings is an area of expertise that we've been involved in for many years, and the painting and coatings department keeps going from strength to strength as we invest in new technologies such as scan electron microscopy. And superyachts we have a superyacht investigation department and consultation department, and they're headed up by master mariners and our naval architects and experienced marine engineers. So move on to our laboratory and technology services. So the Brookes Bell laboratory was opened, built in the midst of the pandemic. And whilst it was quite challenging to build and then open a lab in the midst of the pandemic, we achieved this last year. So 1 year ago in January, we opened the Brookes Bell laboratory, which is based in Birkenhead by Liverpool in the UK. And so that's a regional centre of excellence for fuel testing, metallurgy, material science, non-destructive testing and failure investigations. We initially did have a smaller metallurgical testing service. Since 2013, based on demand, we then decided to expand the testing capabilities to meet the kinds of needs that our clients were expressing during the wider group's marine casualty investigations. So whether you can see some of the fuel testing services, that's an image of the fuel testing laboratory. So the fuel testing laboratory has gas chromatography, mass spectrometry, and a few other really advanced methods of inspecting fuels. And so they work hand in hand with the bunker team on forensic analysis. So to bring you into the subject matter for the presentation, so I'm here to discuss the future in terms of materials testing and non-destructive inspection methods. So this is part two of the presentation is going to be the innovation in materials state evaluation. So we're going to touch base on the conventional methods that are used in assessing material state, the way in which class use them to evaluate global and local strength characteristics of a ship in service. And then we're going to move forward into our new innovations and the ways in which we've been working with class, specifically LR class, at the moment to gain endorsement and qualification for the methods that we're developing. So I'm sure everyone's used to seeing this type of scenario during dry docking and overhaul periods. And sometimes it's unplanned and unwanted. Other times it's much needed. So the kind of areas where we typically encounter corrosion, which would warrant steel renewal, are under deck, such as anywhere, so the galleys, anywhere where there's teak, bollet deck, there's any composites, vehicle decks on vessels, and wet decks, sin deck, all these areas we'd often encounter corrosion. The internal compartments, so wet decks, accommodation blocks, and then more commonly come into contact with typical corrosion issues in tanks, some of the protective paint coatings, corrosion scabbing and blisters, and cargo hold plating on such vessels as bulk carriers, and general cargo vessels on the tank top, the sloping hoppers and bulkhead stools. And then also on every vessel, the whole shell and bottom plating. So class, so I'm presuming that most of the listeners here have experience of annual intermediate or special surveys for vessels. So the conventional methods that are utilized for corrosion assessment and remaining thickness assessment to allow for global strength calculations and local strength calculations to prevent things like buckling is a method called ultrasonic testing. So ultrasonic testing measurement, or UTM as it's commonly known, is used to detect any diminution from the nominal wall thickness of steel. So this is the Classification Society's formula that they usually use for establishing renewal thickness. And with CSR ships, they use the net scantlings approach for every other type of commercial vessel. They use the IACS defined and specific Classification Society defined excessive corrosion and substantial corrosion method, which you can see here. So what you can see here in front of you is the letter A corresponds to the original thickness. So it's the offered thickness of the steel plate that you have on the ship. And the letter B is the renewal thickness or minimum thickness, which is defined by class. And then the letter C defines what we call substantial corrosion. So substantial corrosion is 75% of the maximum permissible diminution. And we tend to see in most areas of the ship, it's dependent on area, but we tend to see the maximum permissible diminution is around about the 30% mark. So substantial corrosion warrants further investigation and monitoring, and that is 75% of that maximum permissible limit. So on most ships, it's around 25% wall loss. And then you start to you have to start monitoring those locations closely during every interval survey period after that. And the lower image you can see here is the standard arrangement for thickness measurements. So you can see here the black dots represent the point measurements. So what happens is a UTM surveyor or NDT technician will attend with a class surveyor. They'll take readings, and then those readings will be used to work out the average wall thickness in a given area. So the types of equipment that are usually used are the ones you can see here in the top right image. So the image on the right hand side shows an ultrasonic flaw detector, and that is used with what we call a 0-degree probe, and that gives you a point reading and a point thickness measurement. On the bottom of the screen on the left hand side, you can see an area that's been prepared to remove scale to take a point reading for UTM. And in the center, you can see a section of steel that's been removed because it's exceeded that maximum permissible diminution mark. So the 30% from the nominal wall thickness or the design thickness. So there's a couple of issues with this type of technique. And as you can see with the previous slide, the point measurements here, they allow for very minimal coverage of the steel plate. So you're taking one point reading, and then for that area that's supposed to account for the surrounding steel, if the class surveyor notices substantial corrosion, such as on the image on the right-hand side, then they will extend the area of inspection, and they'll do a more comprehensive inspection of that region. However, you're still limited to the amount of point readings you can take, and it's not classed as full volumetric coverage. So you don't have a complete view of the material state of that specific plate, that localized section between two frames or close proximity to a bulkhead, or if you're taking into account an entire strake, then it can be very, very time consuming to grid that out and take these small measurements through a large surface area of steel. And what you can see in the middle of that image, just underneath the flaw detector, is a calibration block. So the equipment's calibrated to the steel thickness that is most closely approximated to the design thickness of the steel. And then the UTM probe is placed on the steel, and what you get back is an absolute measurement of that steel. So if we move on to innovation to improve those types of technologies for material state evaluation, we came across many instances whereby ships were going into dry dock, and I'm sure quite a few of the listeners to the presentation will have come across such scenarios whereby you're approaching dry dock, you undergo a standard UTM survey. The class surveyor finds a number of areas which have substantial corrosion, so they have to be investigated further, and then huge sections of plate can sometimes be removed, such as in the image I showed before, which was of a tank top plating in a bulk carriage cargo hold. And the issue here is accuracy and sustainability. So accuracy, if you're taking a 3-point reading for a plate or a 5-point reading in some instances, and then averaging it out, you might be throwing away quite a lot of good steel. So it's not a fully accurate methodology for inspecting ship structural steel. So we looked at different methods to get take full volumetric assessment of steel plate, and we explored various options. And one of the main things is the time it takes in which to scan the steel plate. So the other major factor is coatings and coverings, and the time it takes for a normal UTM company, if class say so, to remove things like teak and bollock deck and wet decks, these areas, and then reinstall them at a later date once the inspection's taken place. This presents a few problems. So one of the problems is again the coverage that you can get once you've lifted the coverings or deck coatings or any of the coating or in any other areas of the ship, and also the fact that you don't know, or you can't preempt the condition of the steel prior to removing coverings. So it's one of the biggest issues, and it heavily affects cost, is that shipyards, operators, and management companies don't have the ability to anticipate where steel renewal will have to take place until they go into dry dock and until they have a periodic survey performed by a UTM company and class. So we looked at different methods, and the coatings and coverings kept popping up as a bit of a blocker for a lot of NDT companies. And then we knew about various technologies that had been created in the 1970s, had over the past 10 years really evolved in tandem with computational involvement. So as computers get better, advanced inspection techniques get better, they get quicker, and visualization software gets better. And we came across, we already had experience with Pulsed Eddy Current, but we came across great utilization of Pulsed Eddy Current array systems, which is another way of evaluating wall thickness, either directly onto steel or through thick coatings. So what you can see here on the right hand side is it's a superior, and it's along the deck, the teak decking there. You can see a heat map. Now that's some real data collected that demonstrates the corrosion underneath the teak decking. Not just identifying corrosion, but it also takes thickness readings, so it takes volumetric thickness readings. And so we, for the past 3 or 4 years, have been developing Pulsed Eddy Current array technique with our equipment providers over in Quebec, and we've developed and coded some fantastic analytical software, which is our CMAP technology. It's we can utilize it across all marine industries. So it's designed primarily for ship structures with coatings that they would like to assess the material state through these coatings without having to remove the coatings and face the costs of preparing areas for inspection. So in the image on the right hand side here, you can see how we utilize the technology on vehicle decks through coatings and often through screeds. So it's a practical and sensible approach to tackling the problem of corrosion, whether it's hidden or otherwise in the marine sector. So I'm going to take a little bit of time to introduce you to the methodology and the inspection method, the technique. So Pulsed Eddy Current array is the system that we use to gather the data. So this is electromagnetics. So whilst the conventional method used for thickness measurement and corrosion assessment is ultrasonics, which is a mechanical sound wave, this is an electromagnetic technique. So it uses electromagnetic wave spectra to analyze the steel substrates on the vessel. So the Pulsed Eddy Current technology was introduced by Shell offshore oil and gas in the 70s, but it was very slow. You'd have a dwell time, so you'd have to hold the probe on the steel substrate for a couple of seconds and take a point reading. The data was very hard to interpret, and of course it was very slow, and it was primarily designed in the 70s for scanning through thick lagging on pressure vessels and pressure systems. Edify Technologies in late 2010s they had been working on this technology for a while, and they managed to develop a quicker way of analyzing the data collected by pulsed eddy current systems. And they developed something called the pulsed eddy current array. So pulsed eddy current array is basically, it is multiple electromagnetic coils paired together to achieve a wide coverage, and also with the advancement of computer technology, the way in which the pulses analyze the data has vastly speeded up. So what you can see there is an array probe that has 6 channels and has about 470 millimeters of coverage. So if you compare that with the 20 millimeters of coverage that a UT probe has, plus the added benefit that it can see through any non-conductive coating, because we're using electromagnetics here. So it's only conductive coatings that would interfere with the electromagnetic signals. So the refining of this technology allows for array capability. That array allows for greater coverage. And then what we've been working on for the past few years is a way to give a full structural steel plate analysis connected with the ship's drawings and the DWG files that the little ship that ship designs inherently have with them. For each deck level, you'll have a DWG file that's usually marked up during a class survey with point readings. So we looked for a way to integrate this technology and overlay and map it onto a 3D model of a ship's structure. So we first achieved 2D model. So we use either shell elevation drawings or deck drawings in DWG file. We create a 3D model of the area of interest. And then what we do is we acquire the data with the pulsed eddy current array electromagnetic testing equipment. And we coded some software that takes that data and overlays it onto the model of the ship, fully rendered and fully accurate positionally. So we'll go into that in further detail shortly, but as you can see, it gives you a great amount of coverage pretty quickly. So you can scan at around 220 millimeters per second with this array scanner here. We've also got various array scanners. So we've had a lot of custom built array scanners made which increase resolution. So what you tend to do is you'll take a pulsed measurement of a specific area. When we multiplex the signals, it's called, we can scan dynamically. So you can scan forward and it's an encoded scan. So all of the data captured is digitally recorded to allow for a robust digital data set that you can then overlay onto your model. What we also coded and developed was the analytical side of this. So the ability to take through wall and thickness measurements and monitor wall loss and identify corrosion accurately to within 100 microns through coatings of up to 100 millimeters. And so the CMAP software that we've developed allows for the data that's been collected on pulsed eddy current to be used by the classification societies, by the owners, to anticipate any areas under thick coatings that may require treatment and steel repair or renewal, and obviously also cost for those in advance of a forthcoming dry dock visit. And in order to, so we carried out quite a few scans on various size vessels, and we did a few in the Ro-Ro-Ro-Pax sector, and we found that they had severe issues with vehicle decks, and they were having unplanned downtime due to going into dry dock and finding these areas of corrosion, or sometimes they'd have freight in high traffic areas, which would actually cause a catastrophic failure and buckling or collapse of certain areas of deck. So we found quite a few clients who were looking for solutions to get a full representative scan of large areas of steel, which is which was otherwise they were unable to get prior to this. So we set out to carry out some of these inspections, and when carrying out these inspections, we evolved the software and worked closely with the ship managers, operators, and the repair yards to really develop the service so that it's easy for them to use. It gives them a tangible feel for the material state of their assets, and they can feed the data to the shipyard and to the classification society for analysis, whether it be repairs that need doing or for global strength or local strength calculations. So we got talking to Lloyd's Register, and they heard about this technology, and we've had and also the UK Ministry of Defence, and we've been pioneering the technology with them and our CMAP analytical software to get the method endorsed by class and eventually qualified for use in the defence sector and also the commercial shipping sector. So to do this, we're going to give you an overview of the technology and some demonstrations now. So what we set out to do with class and Lloyd's Register we're working with at the moment, and the Ministry of Defence in the UK, along with a couple of commercial shipping companies as well in the RoPac sector, is we've got to prove probability of detection. So we have to prove the minimum detectable defects. We have to prove the sensitivity to liftoff. So liftoff is the distance between our probe and the steel substrate. So you could be scanning directly onto opaque coating. You calibrate the equipment to do that, and then it will choose the correct range of frequencies to measure the steel through a thin coating. Conversely, you might have an area of bollet deck or teak decking with rather a lot of liftoff, say 40, 50 mil. You calibrate to that liftoff, and it will select a different range of frequencies that will allow you to assess the material state under a thick coating. So what we've done is we've done extensive field trials, we've done extensive probability detection studies, and we had specifically for LR class endorsement, we've had 4 specimens manufactured, which have a range of flat bottom holes to simulate localized corrosion. And then in the bottom of your screen on the right-hand side there, you can see it's a giant step wedge. So just like the small block I showed you before for the UTM calibration, this is a giant step wedge, and it has different levels of thickness incrementally, 20%, 40, 60, 80. And what we set out to achieve here and demonstrate is the accuracy and precision at each liftoff for every thickness that you'd encounter on a vessel. So what we're going to do right now is we're going to show you some live scan data and the equipment in operation. We've chosen this specimen to show you the live scan data and results of, and this is the step wedge. So this demonstrates the precision, taking thickness measurements, and obviously as a byproduct of that, mapping corrosion. We can change the resolution, so we can pitch the resolution down to around about 5 millimeters in the Y direction. So that means moving forwards, you can take a pulse every 5 millimeters. So you can imagine the amount of data points you can collect over, say, a 6x3 meter plate, steel plate. And then in the output, we'll demonstrate to you the way in which we easily differentiate between various levels of wall loss. And then after the demonstration, we'll then show you the modeling, CMAP software, and our analytical process, and how we can handle large data sets and use our software for class compliance. So what we have here is a live scan demonstration. So I'm going to just introduce Luke Swords, one of our inspection engineers here. He's going to give you a brief overview of the live collection of data.
Good afternoon, everybody. Okay, so as Arron has already explained, pulsed eddy current is an electromagnetic testing technique used to detect wall loss on ferromagnetic materials, such as the carbon steel step wedge that we have here. You've just seen that in the previous slide as well. So if you want to start the video. So PEC provides a relative volumetric measurement based on a calibration area. And this here is going through the calibration process now. The tool itself there is the PEC 7-channel high-res array probe, and that is currently taking a reading now, which we are telling the software and the hardware that it is sitting on 8 millimeters of plate now, so it knows that that is the nominal thickness, basically. Then for resolution purposes, after that, we have to choose how many averaging points or thickness readings, as Arron explained earlier, are taken over the predetermined area. The more readings taken, the higher the resolution we'll get in the data that's produced. As you can see, as we move over now, we move into the increments of the step wedge. That's into 20% wall loss. Then we go into 40% wall loss from there. You see we've got a colour palette set up as well, so we can differentiate between the areas. That now is going into the 60% wall loss area there. You can see the thickness readings as well, the wall thickness measurement readings. And then we go into the deepest part of the step wedge, which is the 80 mil plate. And then we go back into full thickness, which is the 100%. So the second video now, we've got a lift off there now of 30 millimeters. The first lift off was set pretty much 3 mil just above the plate. So we calibrate again in the area, the same area. So the probe knows the lift off, so it can measure to the bottom of the material from the top of the lift off. And when you can see, we start scanning again at the high lift off. We've got identical measurements and readings as we did in the first scan. The different color palettes coming in again. 40% wall loss, 60% wall loss, and in the 80% wall loss again. Beautiful signals, and then back into the 100% wall again. So we can inspect up to lift-offs of up to 30 millimeters plus. Anything over that will produce accurate measurements, but we may lose some resolution in the data. Yeah, Arron, okay.
Yeah, so that was the live scan demo of the step wedge control specimen in our Liverpool-based laboratory here. So you can see the accuracy of the technology and the speed in which you can scan. We can scan quicker than that for the purpose of demonstrations and to achieve a really high resolution. We chose that scanning speed. If you're on a vessel where you just wanted a quick squiz at the material state, and you might want a lower resolution and a quicker scanning speed to achieve more meters squared per hour, then you can adjust the resolution accordingly. And so what you have here is you have what we call a C-scan. So a C-scan is a plan view image of the data set. And so as you can see, the data set in the C-scan image corresponds nicely to the step wedge. And we tend to get it accurate to within 2 or 3% at most liftoffs, which, if you think about it, 2 or 3% of 8 millimeters is only a few microns, really. So the accuracy is second to none. What you see at the bottom of your screens there, that's the first taster view that you've got of our CMAP analytical software. So what we do with the output of the Pulsed Eddy Current array technology, so we capture the C-scan, the plan view, and then we model it. So at the bottom there, you can see the diminution physically in 3 dimensions. You can also see it in relation to the wall loss color palette. So yeah, I'll quickly say, during the video that you just saw there, the wall thickness was displayed on the screen. Obviously, that's the wall thickness, not the wall loss. So where you've got wall thickness 23.4, that's actually 76.6 wall loss. So that's only 3.5% out from your 80 millimeters. And that's at the lower end of the scale. We can get higher and higher accuracy and precision at diminutions down to around about 60 to 70%. And then you tend to get a slight drop in accuracy, but for the purpose of marine inspections, it's pretty much perfect, because you got to remember, in a marine environment, we're trying to identify wall loss approaching 30% and incrementally up to that. So what you tend to do, like I'll just cover what I mentioned before about the substantial corrosion. So 25% of this 8mm plate class would deem that as substantial corrosion. So then that warrants further inspection, it warrants monitoring. And it's not until you get to 30% that you would tend to remove the steel, although quite often the class surveyor will ask for steel to be removed at that point if it's widespread, because over the course of the next few years, the material will most likely go beyond that 30% maximum permissible diminution threshold. So we're going to show you now how we perform these inspections in the field with a case study. So we're switching to our scan zone view. So when we visit a vessel, so one of our clients has been kind enough to let us use a redacted report for a case study to demonstrate how we use the power of the technology, but on a very large scale. So what you could see there was quite a simple scan, and it was quite general corrosion, not localized. Localized corrosion is defined as small areas of corrosion quite closely packed. So when we approach a vessel, for instance, here you can see the vehicle deck of a large RoPax vessel. We split the deck level into scan zones. The scan zones are longitudinally and transversely framed. So we establish a 0-0 position, that's bottom left of the scan zone, and we have an exact coordinate position for the start of each one of those scan zones, and that gets overlaid directly onto our model, and that can be either the shell or anywhere inside the hull envelope, or the tanks, or anywhere around the vessel. This is a 2D view that you can see here, taken from the DWG file of the vessel. Each scan zone is given a unique ID. And then what I'm going to quickly demonstrate to you now is the analysis and reporting. So this is a more complex geometry to inspect in terms of it's got local and general corrosion. So this is the output from our scanning technology over a larger area. So this plate, as you can see, is a few meters wide and a fair few meters long. So this video shows how we crop the data set. So all we're concerned about is the substantial corrosion. So we remove any unwanted data, and then we can use, if you see on the top right of the plane, we can use our technology to identify the X and Y position, so the start and finish of every area of substantial corrosion that is inside that scan zone. For the purpose of this client in particular, and most clients, what they want us to do is cut all the data out that's below 15%. So they want to look at that between 15 and 25% region, which is what you can see here. So that on the basis of this, you can develop a risk-based inspection strategy to monitor those areas. If and when you perhaps apply a cropped insert to those areas, the surrounding areas would still be classed as a risk. So you would monitor them more closely in future inspections. We highlight any areas of concern, and each defect is allocated a unique ID as well. And so within the scan zone, each defect is given a number and is treated separately. And this demonstration here is just showing the way in which we establish the start and finish of all of those defects. And then based on the analysis of the scan zone, what we do then is we perform analytics. We look at the average wall loss within that area of concern. We look at the average wall loss over the entire plate section or scan zone section. we can, once the scans are stitched together, we can look at the wall loss within a given longitudinal frame anywhere across the ship. So for things like global longitudinal strength calcs, where you have to take 3 transverse bands of the vessel during its special survey, say for instance for a tanker over 15 years old, you'd have to take 3 transverse bands. This would allow you to stitch the scans together and get the average remaining thickness and the wall loss for that whole cross-sectional modulus. So for each scan zone, we generate what we call a 5-view report. So there's a little description on the right-hand side in the text there. But what we do is we have an isometric plan view, and then we have an isometric view which gives the client a tangible feel for the kind of the depths of corrosion which are appearing on the plate. And then you have a 2D plan view. The 2D plan view is the plate in its entirety, and that's what most naval arcs or overhaul team would use to evaluate the that given region on the vessel. In the bottom left, it's everything over 15% wall loss. So these are all of the areas of concern together, with everything that's not of concern in this immediate moment clipped. The middle is, as I say, for corrosion monitoring and to develop a risk-based inspection, is 15 to 25%. So from 15% to substantial corrosion as defined by class. And then on the right-hand side, you have all of the areas uniquely identified above 25% wall loss, which in most instances would require a cropped insert or some kind of treatment. If it was on a more excessive scale, like you saw in the model that we were showing then, it may well warrant complete removal and renewal of a plate section. So what we do is we stitch these scans together, we integrate them into our model, and then we have this. This is a CMAP overview. So the CMAP overview is a really useful tool. As you can see, it gives the client a real tangible feel for what's going on in the vessel and to analyze the material state rather than the kind of archaic tabulated values only. So with the tabulated values, you have to look through hundreds and hundreds of sheets of paper sometimes to find the areas which are of concern. So this gives you that overall view for the deck in question. So we'll show you some of the views now. So this is the main vehicle deck on this RoPax vessel. And this is, we can change the palette, we can change the clip, we can do a lot of stuff with the data set to express in a tangible view whatever the client might want to know about the material state. So in this instance, we give a general overview, and then we change the data set to show all wall loss from everything from 100% wall thickness right down to 30% and beyond. Anything over 30% is purple in this image. And then the same as we showed you before with the 15 to 25% and over view, we also provide that as a deck overview. So as I say, this can be applied anywhere on the vessel and through coatings up to, in some regions, 100 mil thick, but 50 mil thick is what we usually come across, anything from 3 mil up to 50 mil. And you can achieve this type of data output. So this is I must say, this is a particularly corroded vessel. And what you can clearly see here is the actual vehicle tracks from heavy traffic. You can see them in the areas where freight is stowed on the vessel, and also running down the most commonly used high traffic areas on the vehicle deck. So this is what our clients find most use of, is this overview. We of course give the overhaul team and all of our clients a tabulated breakdown for the data as well. So we take all of the data sets, and for each scan zone, one by one, we apply our algorithm to it, and it extracts the various data, and it will give us plate section summaries. And also for each category, which you can see in the 5 view that you saw previously, you'll have individual tabulated defect reports. So it'll show you the total test area in millimeters squared, the average wall thickness for that plate. So in terms of being able to integrate the corrosion mapping and remaining thickness calculations into, say, Argonaut, which is Lloyd's Registered tool, we have designed the software to be able to do this, and that's what we're in discussions with class about at the moment. So as an example of the output from the data, you can see here, the maximum wall loss detected within the previous scan zone is 45%, but the average plate thickness is 89%. So in some instances, just based on a 5-point or 3-point survey, or in a lot of instances, those areas of severe corrosion that may compromise local strength or increase the chance of buckling would go undetected. So that's specifically groups like the UK's MOD are really keen on being able to understand these kind of areas that go unnoticed and improve or optimize the efficiency of their vessels and the strength of those. And that brings us to the end of the presentation and the demonstrations. And thank you for your time. And yeah, now for a quick Q&A, if we've still got some time left in the presentation.
Well, I think we're cutting into lunchtime, but I think that's been a brilliant presentation. Thank you ever so much, guys. I find it all very fascinating. So, any questions?
I have one, Arron, is with your 3D modeling, and that, do you have another component that would say, in a situation where there's damage, that you could provide that data to a shipyard to start forming plate or mold shell plating? Is there an extension to that reporting that could be used for repair?
Yeah, very, very much so. That's the one of the most used tools, or one of the byproducts of the corrosion assessment, is that it creates that it covers those type of analytics. So in terms of a shipyard being able to assess the tonnage of steel that needs replacing and in what sections, we can easily extract that data quickly from the recorded data sets. So that's what the overhaul teams tend to use the reports for. So these surveys can be done in service, and we do even have marinized probes. So if you have a dive team, some hull bottom inspections, for instance, can potentially be done in the water. And in terms of, say, the vehicle deck that you just saw then, that can be done 6 months prior to reaching dry dock, a year prior to reaching dry dock. Corrosion rates are only 0.1 of a millimeter a year in a standard kind of marine environment. So the data set that you take 6 months or a year prior to the dry dock won't have changed much in that period. So that's the kind of foresight that it affords.
Mm-hmm. Yeah. No, I find it.
Yeah, go on, Ed. Sorry, keep going, Ed.
No, I was just amazed. We're still doing UT work, and with the probe and the scanning and the ability of the data is just really impressive. I'm actually, I won't say shocked, but I'm really impressed with what you've presented here. Yeah.
Yeah, it's
you're at one of your offices at Houston, is that right?
Yes, we've got an office in Houston and Miami. Yeah,
Miami. Yeah. Yeah. No, I'm gonna look at it closer. I pulled up the website too, just to get a little bit more information. But from a repair standpoint, whether it's salvage or emergency repairs, because I've been looking at 3D scanning from hull shapes. For repair work, and when I look at this, it's just an extension to, it's the early extension to what So
that's something we engage in quite a lot as well as 3D scanning. So 3D laser scanning and 3D mapping, especially for repairs on vessels. This technology lends itself specifically well to that. In fact, you can theoretically integrate the two together, creating a point cloud and overlaying the data onto the 3D model, which is something we're working on at the moment.
Yeah. Where are you located? In Houston? Are you in Houston or are you in?
No, so we're in the UK in Liverpool. Yeah.
Okay, well, that's great stuff. I'm gonna take some more time and really go through your presentation, and I'm sure you'll hear from me.
Yeah, feel free to reach out, and we can provide a more focused presentation and demonstration to suit your specific requirements.
I've got a question posted through chat. Do you also measure vertical plates?
So yes, so in terms of the inspection itself and the modeling, it can be done on the horizontal or vertical plane.
Okay.
So it's, I mean, you tend to, that image you saw there could easily be shell expansion, for instance.
Sarah, you've got your hand up. You're muted, Sarah.
Are there any areas where it's difficult to apply pulse eddy current testing?
Yeah, so there are some limitations to the technology if you're in areas with severe vibration. So, for instance, if some areas in an engine room, if the ship's functioning or the generators are on, you can get some interference through vibration, and that can induce DMF. But in most conventional areas, no. If you wanted to look at structural members, you can do that too, but you won't get the same kind of the mass collection of data for those. They're more strings of scan data. So, but they can be applied to structural members as well. But for limitations, it's as long as there's no conductive coatings, that's the main thing. The probes can see through thin galvanized steel, thin stainless and thin aluminium coating. So things like weather jackets and stuff like that, or some types of insulation and heat covering. But generally, most inspection surfaces are non-conductive, or coverings are non-conductive, and it can see easily through those.
Thank you very much. That was an extremely good presentation. Thank you.
And the Beatles?
Hey there. Is it of any use with carbon fiber?
No, so just to go into a bit of detail quickly about the way it works. So the pulsed eddy current works off induction. So what we do is we induce eddy currents through an excited pulse into the steel substrate. So the fact that the steel's ferromagnetic, it causes a secondary field which allows us to magnetize the component. And what we actually do is we monitor the transient decay, the electromagnetic field. So the quicker the field decays, the thinner the material. The thicker the material, the slower it decays. And then we build sizing curves based on that. So it's, although some carbon, although some of those materials are conductive, we can't use pulsed eddy current on them because they're not ferromagnetic.
Thanks for that.
Answer everyone's questions.
I have one question. This is Dwight from Capilano.
Hi, Dwight.
Vancouver. I often deal with surfaces that have sporadic pitting in them. So you'll find full thickness until you'll get that. It's usually under microbial induced corrosion areas and whatnot. I'm wondering, and I saw the charts that you show, the images that you show seem to have and I know it's not, but seem to have an infinite precision, say. So what's the limitation on picking up things like?
That's a really good question. And yet again, in fact, sorry, relating back to the previous question, that is the limitation is it's designed for, you can do a low resolution, high volume of scanning. The technology itself is not for small defects. It takes a volumetric calculation of under the footprint of the probe. So even though we can increase the resolution, the smallest defects you can detect are down to about 10 to 15 millimeters. And it's not really designed for those to focus on that type of defect, or between that and say 50 millimeters diameter. You would have to scan at a really high resolution, and it would take some time. Although we've got custom probes built for smaller pits, generally, because it takes a volumetric measurement, so that's the footprint of the probe. It's not usually used for mapping out really discrete defects.
Thanks, Graham.
So Ed, I think we probably need to draw a line there, don't we? And
Yes.
thank the guys at Brookes Bell. I'm just going to stop the recording.